backpropagation and how to derive this particular backpropagation layer by layer. So was it shown? Okay. Acha. Second is implementation. Suppose from scratch. If I, Mr. Amar, what is that? No. No is for no derivation or no coding. Acha, it was shown in simulator. Okay. And backpropagation, that derivation was shown. That exactly that chain rule. Chain rule, yeah, somehow. Okay, so let me just recapitulate it once again. I think it will help you in understanding it much better way. Okay, so that layer by layer, how this particular computation is being done, and this is a very simple math, very simple math. Okay, so you have to just keep your mind open. Okay, I think you will be understanding. Okay, so let me just start with that. Acha. Next is that I'll be showing something regarding just 1 second that how to implement this kind of very basic neural network, okay, from scratch, okay, using only NumPy, and then I'll be showing something using this particular PyTorch, that how to actually implement in this Torch framework. Torch is actually based on tensor based framework. Okay, so this is basically you are not this particular whole network can be represented as a tensor. I think many of you understand tensor. What is tensor, by the way? I'm not going into physics-based explanation. I'm going to understand that what is the maths-based explanation. Can anybody tell me what is tensor? It's a sorry, Mr. Amar wrote it's a library in Python. No. So I'm asking that what is tensor, by the way? What do you understand by tensor? Anybody? So used to represent data in multi-dimension. Yes. So this is basically if you look at this particular vector. Okay. So vector is basically having one dimension. It is basically generally we are going into matrices and vectors. Okay. So in matrices and vectors, basically vectors are those matrices. Okay, whose one particular dimension will be 1. And the other dimension will be 1 or more than 1. Okay, so if it is having both of the dimensions as 1 cross 1, as 1 cross 1, then it is actually a scalar quantity, right? So let me just write it out. So let me start. So before that, just give me 1 minute. Actually, I wanted to show something regarding from scratch how to implement using only Python. Using only NumPy, not using this PyTorch and all these things. Just 1 second. Actually, I'm not finding it out right now. I don't know where have I kept that particular code with me. So, okay, I can. Yeah, I think I have found it. So, basically, if you look at this, so can you see my slides? Can you see my slides? Anybody? Can anybody please confirm me?
Yes, sir.
Okay. Okay. So generally, what happens that neural networks are the core of deep learning. Okay. Core of deep learning. Okay. So first of all, this one and neural networks computation. Okay. So neural networks, you can say it is a it is an elegant representation of computation uh, of vectors and matrices. Okay, and based on that, basically, this whole thing is being done. Right. So first we need to get little bit clarity on what are the vectors, then matrices, then this thing, then basically the tensors. So tensors are basically multi-dimensional array. Okay, more than in many of the cases, and or in most of the cases, it is basically multi-dimension, more than two dimensions. If it's happening. So so vectors are basically uh, we write it, yeah, we write it like n cross 1. Okay, so r means real numbers. N cross 1 means that n number of elements in that particular thing, a particular vector, and so n rows basically, and one column. Matrices are basically are n cross p, means I am having both of the dimensions, um, both of the dimensions of that particular array as more than one. Okay, in most of the cases. And tensors are actually having multi dimensions. Okay, so n cross p cross m cross b, like this it is going. Okay, so more than two dimensions if it is having, generally we call it as a tensor. So tensor basically you can come back to vector. If you are having only two dimensions, so you can represent it. Now there are two popular frameworks in Python, okay, as well as in R programming also, by which you can implement these neural networks. Okay, so one is known as TensorFlow, okay, and another is called as PyTorch. Now you can implement, it is not mandatory that you have to use this one of these two packages. Okay, no need of it. You can do all the things using NumPy. Very basic kind of thing. Okay, you can actually do. So from scratch, if you want to code, you can use that particular simple NumPy, because at the core, or you can say at the center, this neural network computation is all about this vector matrices multiplication, matrix multiplication, addition, and that's all. Okay, in most of the in almost all of the neural network computation, okay, it is all vector vector matrices or tensor kind of computation, tensor kind of computation. And mathematical operations are only product, product, sum, product, or sum. Okay, so these are the mathematical operations basically we are using. And in another thing basically which are important for neural networks, that is basically the sigmoid functions. Sorry, not sigmoid functions. In general, it is the activation functions. Okay, so activation functions. So there might be different types of activation functions. There might be different types of activation functions. So through which layer, output of one layer is passed through this activation function, and it will be the input to the next layer. Okay, so activation functions. Now in activation functions, we can have sigmoid, we can have tanh, okay, we can have ReLU, we can have leaky ReLU. How many of you have come across this particular term? How many of you have come across these particular terms? Yes, Mr. Amar. Anybody else? Anybody else? Anybody else? Have you come across these particular terms earlier? So there will be leaky value. There will be. It can be actually. It starts with. I have actually missed the most basic one. That is the linear one. Okay. So linear. So in the last session, was it not discussed where these particular activation functions were not discussed? Okay, so let me just give a brief of this all this activation function. Yeah, one term is tan sine. So that is basically tan. It's not tan sine. It is tan inverse or tan hyperbolic. So can you please verify that? Tan hyperbolic. Yes, activation functions. So yeah. So I'm just giving you a brief of this particular activation functions and how it is basically used. Okay, so let me just give a just recapitulation. So neural network architecture, basic neural network architecture. That is neural network architecture, and that is known as multi-layer perceptron or perceptron. Okay, multi-layer perceptron or perceptron, simple perceptron. So basically what happens here, that there will be an input layer. So this will be input layer. Okay, it will there will be some hidden layers. Okay, so this is one hidden layer, this is another hidden layer, a hidden layer. So like this. So suppose this is the output layer. So two hidden layer. So hidden layer 1 and hidden layer 2. Okay, and this is suppose output layer. Now the thing is that uh, in general case, in general we are having a fully connected kind of neural network. Okay, fully connected. Acha, here fully connected. Yes, yes. Okay. Now this one to this one to this one to this one. Okay. Then this one to this one to this one to this one. Okay, so in this way, basically fully connected. Okay. Acha. Now what happens that this one, and this one. Now suppose what happens that this is our x1 variable and this is x2 variable, which are the input variables, and this is suppose a case. Okay, this is suppose a case of suppose instead of two nodes. Okay, suppose if it is a single node, I'm just telling you to imagine. So then generally in it happens in case of continuous output. Okay, so output can be continuous or discrete. Okay, and discrete can be two class or more than two class. Okay, so it can happen. So now what happens that suppose if it is continuous, then we call it as a regression problem. If it is a discrete one, we call it as a classification problem. Classification problem. Okay, now what happens that these input layers, okay, from these input layers, this input data is uh, basically passed to the hidden layer nodes first. Okay, so what will happen, the input to this hidden layer, okay, input to this hidden layer will be the summation of this weight multiplied by the input values. Okay, so if this is suppose, so hidden layer 1, if I am telling, so this is suppose the weight, it is connecting from uh, input to hidden 1. Okay, and this is 1 1. So this is suppose 1, this is suppose 1, this is 2. So some kind of complex notation will be coming, but it is easy. Once we are able to follow, then it will be easy to recapitulate or replicate. So input variable x1 is sending its input to the first hidden node, first layer. first hidden layer, first node. Okay, so it is given as W from I to H1 and connecting 1, 1. Okay, similarly, the second one is WIH1 and it will be 1, comma 2. Similarly, this will be WIH1 1, comma 3 and this will be WIH 1, 1, comma 4. Similarly, suppose if I tell this one, so this will be WIH1 2, comma 4. Okay, this will be WIH1 2, comma 3. Okay, in this way, basically it will be going. So in this way, now the thing is that the input that is collected at hidden node 1, that will be sum of WIH1 1, 1 plus WIH1 1, 2. Okay, so input at hidden 1 node 1 will be WIH1. Achha, I have to keep some space here. I have to keep some space here because some more nodes will be coming. So that for that, so input at hidden 1, node 1 is WIH1 1, 1 x1 plus WIH1 2, 1 x2. Is it okay? So it is written like, so in form of summation you can write. So similarly, node 2, it will be WIH1 1 to 2 x1 plus W uh, IH1 2 to 2 x2. Okay, now this is input at hidden node, layer 1, node 1. Okay, that is the input. Now at every node inside every node except this particular in every hidden node, actually what happens that first you will be summing up, okay, the inputs, all the inputs you will be summing up, and then you will be passing it through the activation function. So this is summing up, okay, and this is passing through activation, okay, and that will be, so that will be the output. Okay, so O, that will be the out. This is input. Okay, so this is what that is done in every hidden node. Now the thing is, there will be a node at each hidden layer. Okay, so there will be a node at each hidden layer, okay, which will not be connected to the earlier layer nodes. So that will be known as bias node. Okay, so we will be calling it as bias node. Here also bias node. Okay, so what is the input in this? It will be 1. What will be the input in this? It will be 1. And this bias node will be connected to all the next layer node. So here also it will be connected to the next layer nodes. Is it okay? Now why this bias node is kept? Can anybody tell me? Can anybody tell me what will be the what is the use of bias node? Can anybody tell me what is the use of bias node? Why do we give this particular bias node? Mr. Amar, Mr. Amar, can you please tell? Okay, so now this input at hidden node 1, that will be passed through the activation function. and shifting act. Shifting act, by that, what do you understand? Can you please explain? So pass through activation function, and this will be input to the next layer. Okay, so why this bias node is kept? Okay, that is having one reason, that suppose all this summation and active after activation function, after passing through activation function in hidden layer 1, okay, for all the other nodes, the values coming out after activation function, it is 0, suppose. Then what will happen? That all will be going to be 0 0 0 0 0, that kind of something. Okay, it might happen. So in that case, what will happen? To avoid 0, there will be a bias node. Okay, there will be a bias node which will be having input 1. Okay, and which will be having some kind of weight, which will avoid the next layer input, some of the next layer input uh, to any node in the next layer. That will be that it will be avoiding it to be 0. Okay, so some non-zero value actually will be getting. So that's why this bias node is actually kept. And this bias node, okay, bias node is same as bias node, playing the same role as intercept in regression. Okay, bias node in any layer is basically intercept in, that is playing the role of intercept in the regression. Okay, now the thing is that where from this particular regression is coming into picture, and how it is actually related to regression. It is, take any hidden node you take. Okay, then what will happen? That it is actually summing up. So input to that, it is summing up all the coming out, all the outputs from the earlier layer. Okay, they are summed up, and they are actually passed through a particular activation function depending upon our choice. So here what is happening, that each node is actually computing in a regression form, and this is basically multi-layer nested regression model. Okay, this is what neural network architecture in of the basic nature or basic structure. So this is multi-layer perceptron. Okay, now perceptron. Okay, now next is that this is a feed forward network. Okay, so this is a feed forward network. So what do you understand by feed forward network? Means we are, from input side, we are actually feeding the inputs to the in a forward way. Okay, so it is moving in the forward direction. And so one is your feed forward, and second is your back propagation. Okay, now what is this back propagation? So what happens, that you have got the output at this output layer. Okay, this is the output layer, you have got the output, so you have to compare it with the actual output. So here what happens, that compare actual output with predicted output, and that will give you the error. You can actually compute the error, okay, based on the actual output and the predicted output. Now if it is a regression problem, then we'll be going for SSE kind of error computation. If it is a classification problem, then we'll be going for entropy loss, cross entropy loss. Okay, we can go for softmax. Okay, this kind of functions actually you can use. Now looking at the activation function, so let me just tell you that what are the activation functions they are available. Okay, so very first is linear. Okay, so it is input equals to output, or you can say output equals to input. It is output is same as the input. Okay, next is, yeah, y equals to x kind of. Okay, So whatever is coming in, it is going out. So this one. Now next is sigmoid. Now sigmoid is basically 1 by 1 plus exponential minus z. Means if z is the input, okay, so here this is the output. So output is this one, input is z. Achha. And what is the kind of what is the you can say what is the form of this particular sigmoid function? It will be, so let me draw that also. So this will be between 0 and 1, and it will be coming like this. Yes. Okay, so it will not be touching the axis. Okay, so it will not be touching the axis. It's basically nearly touching, asymptotically touching. Okay. Achha. Now C, that is tan hyperbolic, tan h. So this will be exponential of z plus exponential of minus z, okay, divided by exponential of z. Sorry, this is minus. In the numerator, it will be minus, and in the denominator, it will be plus. Is it okay? This is just a modified version, okay, of sigmoid. Now here it will be, here it will be, here it will be. What will be the upper limit and lower limit of this particular function? Can anybody tell me? What will be the upper limit and what will be the lower limit of this particular function? Can anybody tell me? It will be from -1 to +1. -1 to +1. Very good. So -1 to +1. And the functional form will be like this. It will be going like this. Okay. Next is ReLU. ReLU full form is rectified linear unit. Okay. So ReLU of, suppose, input x, it will be max of 0, x. Okay, and it is a kind of very hard function. It will be kind of it will be going like, I'm using a different color. So 0 and x. Okay, so is it okay? So at 0 and below 0, it will be 0. Okay, and after 0, okay, it will be as x. Is it okay? Okay, so this is ReLU. Next is next is next is your LU. Okay, so okay, first before that, let me write leaky ReLU. Now leaky ReLU, what is actually what it is telling? Okay, it is basically telling that it is 0. Sorry, it is x. It is x if x greater than 0, and alpha x if x otherwise. So here what will happen, that instead of being at 0, at you can say at 0 or below 0, instead of being at 0, okay, it is actually having this kind of form. So on this side it is like this one, and this side it will be very small. Okay, so very small kind of thing. Okay, on the negative side. So this will be leaky ReLU. So this is sigmoid, this is tan h, this is ReLU. Okay, and then we are having this one, CeLU. Okay, oh, it is Just one. It is Relu, then Elu. Okay. Elu is x if x greater than 0, and it will be alpha, okay, e to the power x minus 1 otherwise. Okay, and it will be kind of very, you can say, kind of having little curvature. Okay, so then EFG, then prelude. Okay, so prelude is actually quite similar as prelude is quite similar as leaky relu. Okay, so in this way, there can be different types of different types of activation function. So where this activation function is actually used, so it is only used in case of so hidden layer node. Okay, so it is in hidden layer node. One side it will be summing up all the outputs from the summing this sum product of weights and all the outputs from the last layer nodes. Okay, and then that will be the input, and then that input will be passed through passed through an activation function, and it will be giving the output. Okay, so in this way. There are some other activation functions also. Sorry, it has not come. So whatever you have written till now, so that has not come. Okay, so I'll be filling it up later. So activation functions. So next is that let me go to this back propagation little bit. Okay, so back propagation for just 1 minute. Let me save it first. So just derivation of this particular back propagation. Okay, derivation of this back propagation. So we'll be use something called as chain rule. Was the chain rule discussed in the last session? Chain rule, was it discussed in the last session? No. Okay, so in chain rule, basically what happens that if you look at this particular output layer, and if it is suppose having only one node, that means it is a regression problem. Okay, so basically it is a continuous output problem. Okay, so we are using the error criterion at the final layer or output layer node, that is SSE, and SSE is some half summation of yi is actual output, and yi hat was good. Okay, right? Now the thing is that what you are going to do that here acha, few of the derivations that will be required. Okay, so here what happens that yi hat, okay, yi hat, it is a, what is that? That is nothing but predicted response. And predicted response, if you look at, okay, so predicted response, if you look at, so suppose for this particular output node, what is the predicted one? Predicted one is basically summation of weight sum product of weight and the output of a particular node in the last layer. So in that way, we are actually calculating. So just set up the notations first. Okay, so let me just do a simple network, small network. Let me just take. Okay, so uh, this is one, this is two, this is three. Okay, three nodes, and this is suppose hidden layer, node A, node B, and this is suppose node Z. Okay, and here this is x1, this is x2, this is x3. Let us do one hands-on, okay, hands-on example so that you'll be understanding. So this will be w1a, this will be w1b, this will be w2a, this will be w2b, this will be w3a, this will be this will be w3b. Okay, and I'm not using any bias node here. Okay, okay, let me use that also. So should I use bias node here? No, it is leaving it out. Okay, no issues. Now, this is the weights are A Z W A Z and W B Z. Okay. Now, what is happening? So this is the node. This is the structure. Okay, and let me just give you this particular. Yes, chain rule is gradient descent means how it allows us. Yeah, yeah. Okay, so that is gradient descent. Yes, so it has become gradient descent. Yeah, to compute the gradient. Yes, and that gradient, why it is important for us? It is important for us to update the weights. Okay, because we cannot do anything regarding. So suppose the prediction. Okay, so prediction at the final node. Okay, so prediction at the final node. Yeah, updation of W. Okay, so prediction at the final node. It is suppose, so I'm taking this particular thing is having, or suppose in the hidden layer, there is one bias node. Okay, so this is bias. Okay, and it is going to this with weight as W0Z. Okay, now the thing is that you have got some predicted value at the output node, right? So what will happen that this prediction is suppose very far from the actual value. Okay, so that means your error is high. Okay, prediction error is high. Now what will you do with that prediction error? Prediction error, basically now you have to send it back to the up to the input layer in some way that in the next step when the computation will be done, then the prediction will be little bit nearer to the actual output than the current one. So basically this current, okay, this is the prediction suppose, and y actual, okay, okay, this is actually greater than, okay, it should be greater than y hat next minus y actual. Okay, it must be, otherwise, so this must be greater than, okay, so we can tell that this must be greater than the y next prediction minus actual. How to do this? That means you have to change this prediction, right? Now prediction is dependent upon, so y hat is, what it is dependent upon? It is dependent upon the input layer, input layer, mm, input layer nodes, node values. Okay, that is the input values and weights at different connections. So either you have to change the input value, either you have to change the input value or you have to change the weight. So either you will have to change the input or the weights. Now input value, if you are changing, then whole problem will change. So input value cannot be changed. What you will be changing? Weights will be changing. That means weights needed to be updated. Okay, so input values cannot be changed. So weights are updated. Okay, so weights are updated. So I think you'll be able to understand this, or should I write it once again? I think I should write it once again. So either you can change, the input values, okay, or you can update the weights. So input values are not changeable. So update the update the weights. Okay, so weights need to be updated. Okay, so weights, now how to update this weights? Weight new at any layer, okay, any between in between connection will be equals to W old, okay, then minus, okay, then eta is the learning rate multiplied by del uh, this particular error function, okay, del W, okay, and it will be at the new value. Okay, so that is basically, that is the gradient you want to calculate, and that is basically what it is now coming as gradient descent. Okay, now the thing is that, let me just go through mm, fully, means just let me write down the data points. So x naught equals to, acha, another one, let me just do this. Okay, so here also I am giving, generally in input layer bias is not given, okay, but here let me give one. Okay, so this one, okay, so this is bias. So here this will be W0A and W0B. Okay, so x0 is 1, x1 is 0.4, x2 is 0.2, x3 is 0.7. Then W0A is 0.5. These are the now these weights are the basically starting values. So somewhere we have to start. So starting value. So 0.6, W2A equals to 0.8, and W3A equals to 0.6. Then W0B equals to 0.7, W1B equals to 0.9, W2B equals to 0.8, and W3B equals to 0.4. And then W0Z equals to 0.5, WBAZ equals to 0.9, and WBZ equals to 0.9. So how actually we are going to do this feed forward calculation? So feed forward calculation, input at A. Okay, so input at A will be W0A multiplied by 1. So input to bias node is 1. Okay, plus W1A into x1 value, W2A into x2 value, plus W3A into x3 value. Okay, so in that way. So input at A will be W0A multiplied by 1, W1A multiplied by x1a plus w2a multiplied by x2a plus w3a multiplied by x3a. Okay. Similarly, input to B will be W0B multiplied by 1 plus W1A into X X1A X1B plus W1B 2B multiplied by X2B plus W3B multiplied by X3B. Okay, so this is the input, and this input on A, it is coming as 1.32. Acha, okay, so you can actually go on calculating these things. So similarly, what I am going to do, that what is the output of A, and I am using sigmoid function. Okay, so I am using sigmoid function. Okay, I'm using sigmoid function. So this will be 1 by 1 plus exponential of minus 1.32. Okay, and this will be coming as 0.7892. Okay, 0.7892. Similarly, net B, okay, so input at B will be 1.94, sorry, 1.5, 1.5, and output of B will be 1 divided by 1 plus exponential minus 1.5, that is point, uh, 0.8176. Okay. Similarly, input at Z, okay, that will be coming as 1.9461. How it is coming? It is actually coming as W0Z multiplied by 1 plus WAZ multiplied by XAZ, and XAZ is nothing but 0.7892. Okay, so in that way, then WBZ is and XBZ. Okay, so this is W0Z is 0.5 multiplied by 1 plus WAZ is 0.9 multiplied by 0.7892 plus 0.9 multiplied by 0.8176, and this is coming as 1.9461. Okay, and out of Z equals to 1 by 1 plus exponential minus 1.9461. Generally, what happens that at output layer, generally we don't go for this activation function. We generally don't use the activation function. But here, suppose I am using, okay, suppose I am using here. So this is coming as 0.8750. Okay, so this is feed forward calculation. This is feed forward calculation. Is it okay? Feed forward calculation. Now, feed forward calculation for this one set of input. Okay, one set of input for this particular input. This is the feed forward output. Okay. Achha. Now the thing is that actual output is supposed. So actual output. So actual. This is the predicted one. So this is the predicted output. And actual output is suppose 0.8. Okay, so here from here you can get it that SSE is 1 by 2 summation of yi minus yi hat. So this is becoming, so I am having only one set of input output pair, so it is 0.8 minus 0.875 squared. Okay, so this is the SSE. Okay, got it? So in this way, we can find out. Now the thing is going for back propagation. Okay, now going for back propagation. So in back propagation, basically, back propagation steps I have to find out. So chain rule for back propagation. Are you following this? Are you following this? Any kind of, if you are having any kind of doubt, please tell me.
Sir, previous slides, sir, please go in previous slide. सर ये थोड़ा इसमें कंफ्यूजन ये है, सपोज आउटपुट फर्स्ट के लिए आया इसका एक्टिवेशन फंक्शन विद यूजिंग sigmoid function 0.780. You have taken this output
0.8750.
0.780, right? First
No,
wala
which one? Oh, acha, this is for layer from input layer to hidden layer. It is from, so here, okay, let me just tell. So this is actually 0.7850 on the input side. Then passing through this particular, sorry, एक minute, 1.32 at the input side. Okay, so just 1 minute, ये गलत लिखा मैंने. So this is 1.32. Okay, so here it is 1.32 at the input side, and output side it is 0.8750. Similarly,
0.780 na sir, after output.
7892.
0.780 first one.
0.7892. 0.7892. This is 0.7892. Okay. Next is input is 1.5 and output is 0.8176. Yes. And okay.
Similarly, third one is
input is minus 1.94. Sorry, 1.9461. Input is 1.9461 and output is 0.8750.
Actually, I want to understand that what is 0.5 multiply 1, where this figure is can point last how we calculate the Z for Z.
0.5 multiplied by 1. Okay, so it is given here. This is the data given here, that this is the initialization. Okay. W0Z. Okay, so from bias node to the output node, the weight given as 0.5.
Okay.
Initialization.
Okay, and bias value is 1.
Bias ka input to any bias node is always 1.
Okay. And
okay, so here let me write it. Input, yeah. So and let me very good.
Yeah. NAZ is how to calculate NAZ? Okay.
AZ.
WAZ.
Here
okay.
also.
WAZ. But okay.
Yes.
Actually, the understanding is that it is not clear that it is written like what it is read as N.
Okay.
WAZ.
Yes. So input value to bias nodes is always 1. Okay. So it is always 1. So that's why the bias node weight. Okay. So W0A is bias node to A. That connection weight. Okay. And input value is 1. So that is W0A multiplied by 1. Then W1A multiplied by X1A. Like this it is going. Okay. Any doubt? Thank you for asking. Okay. Acha. Now coming to chain rule for back propagation. Okay. So basically what will happen, that we'll be taking the prediction. Okay. So we'll be taking the prediction.
Sir,
yeah, please.
Confusion is not.
Please.
Previous is the 1 minute where you have drawn the figure input man.
Yes.
This one. Here you have written 1.32 oblique 0.7892. It means the output
this
is 0.7892, but input is 1.32, means sum of all the x1, x2, x3.
Exactly.
Along with plus 1.
Along with the bias.
Okay.
Okay. So W0A multiplied by 1 plus W1A multiplied by x1, then W2A multiplied by x2, then W3A multiplied by x3. So this is
then again next
next also
slide.
again in the same way. So
Next slide में जाइए,
एक minute. Let me write it here so that you will be able to understand it later also. So W1A x1A plus W2A x2A plus W3A x3A. Okay. Similarly, this 1.5 is written as W0B into 1 plus W1B.
इसे सबका सम अप करके देन +1 करना है ना बाय से,
Exactly. Then you have to pass it through the sigmoid or any kind of activation function. Then W.
Okay, it is right. Then okay, ठीक है.
Okay. Acha, in next slide, tell me where.
Then 1/2 y minus y square.
Hidden to output.
ठीक है, hidden to output. This is error ना. This is the error that नहीं स्क्वायर आपने सही किया, y minus y का स्क्वायर होना चाहिए था, whole square.
Yes.
ठीक है, okay.
It is having only one input-output combination, so that's why it is. I'm not having many other combinations. Only one combination I'm having. So actual y is 0.8.
So ये half क्यों किया? सबका
That is SSE is actually written in this way. Why? Because मैं जब del SSE del beta whenever I'll be calculating, then what will happen? That 2 will be coming. Okay, because it is square term. ठीक है ना? तो एक 2 will be coming. So 2 by 2 that will be actually
हाँ,
1.
nullify करने के लिए वो nullify
nullify हो जाएगा. Okay, means 1 हो जाएगा. Not nullify actually. 1 हो जाएगा. Okay, so this is how basically we are deciding. Okay, so it is up to you. You can use half. You can remove that also, because SSE, if you are using the same functional form, then it will be for all it will be same. Okay, so it is not going to change. Achha, next is chain rule for back propagation. Now we are so is it okay now? Can I proceed? Mr. Umesh has told something. Can you please come online? In previous slides, in the graph of sigmoid function at input 0, it is shown as touching to 0. Its output value should be 0.5. Acha. Okay.
Under
the
slide, that's different.
So actually, ye wala. So it is correct. It is not correctly drawn. Let me draw it correctly. Okay, so this is not a correctly drawn curve. It will be so here it is 0.5 and it will be going like this actually. Okay, it will be going like this. So 0 here and 1 here. Okay, so this is sigmoid, not this one. Okay, so this, you don't look at this. Is it okay now?
Okay, sir. Thank you.
Yes. As a chain rule for back propagation, now we are starting at SSE. Okay, at the output node. So SSE is half of summation of yi minus yi hat whole square. Okay, so del of SSE, okay, right, del yi hat, okay, or y hat actually, it will be used as, it will be coming as 2, okay, so that will be minus summation of yi minus yi hat. Okay, but now yi hat is actually in terms of some other things, because this is a nested sum. So next is that sigmoid function. Yesterday or before yesterday I showed you that sigmoid function derivative is a very interesting one. Sigmoid function derivative. So sigmoid function I am telling keeping as sigma z. Okay, so sigma z is 1 by 1 plus exponential minus z. Okay, so del sigma z with respect to z will be sigma z into 1 minus sigma z. Okay, So now at the output layer, okay, so output at Z, so it is basically 1 plus exponential of minus input at Z, isn't it? Output layer, what is the output? Output is actually sigmoid function passed or the input to that node passing through sigmoid function. Is it okay? Right? So yeah, so at the output layer, Iz is W0Z plus WAZ O of A, output of A, node A, plus WBZ, output of node B. Just try to find out here. So XAZ, what is that? That is nothing but OA. This is nothing but OB. Output of A and output of B. Okay. Achha. So now we are coming to at the hidden layer. At the hidden layer, suppose if I look at output of A, it will be given as 1 by 1 plus exponential of input to A. Similarly, output at B, it will be 1 by 1 plus exponential of minus IB. Now, what is IA and IB? So, IA at the hidden layer, IA will be W0A plus W1A x1 plus W1 2A x1, sorry, x2, sorry, then W3A x3. Similarly, IB, so I means input and O means output. So IB is W0B plus W1A, W2A x, sorry, this will be 1B. This will be 1B. This will be 1B x1 plus W2B x2 plus W3B x3. Okay, so these are the inputs. Okay, now what we are going to do, that output layer to hidden layer, output layer to hidden layer. Let me see that how exactly this. What is the weight updation rule? So weight updation rule. Weight updation rule. Okay, that is given by W new is equal to W old minus eta, that is learning rate, multiplied by del SSE del W old. Okay, this is the update rule. Is it okay? Anybody is having any doubt? Please tell me. So this is new. Is it okay? So this del SSE del W old we have to find out for each of the weights. So output layer to hidden layer first. So output layer to hidden layer, I want to find out how many weights are there. That is 0 W0Z. Okay, this one W0Z, WAZ and WBZ. Okay, so del SSE W0Z. Okay, so this will be given by how I can actually write it. W0Z, where it is coming? It is coming in the input. It is not coming in the output. So what I have to do, that I have to, so but the derivation is the differentiation is actually SSE with respect to W0Z. Is it okay? Just try to understand this first. I am interested in finding out del SSE del W0Z. But the thing is, SSE is dependent upon OZ. SSE is actually dependent upon OZ. This day YI hat is nothing but OZ. So it is dependent upon OZ. It is not dependent directly on W0Z. And W0Z is actually a function, actually an element of IZ. So what I have to do, that del SSE del OZ, first I have to do. Then OZ is a function of IZ. OZ is a function of IZ. So del OZ, that is a function of IZ. Now IZ is a W0Z. Okay, so del IZ is a function of del W0Z. This is called as chain rule.
सर ये ना बैक में जाके जो फिगर हिसाब से जो बना था उसके हिसाब से इसको वापस अगर रूल
okay.
फॉर बैक प्रोपगेशन उसको
हाँ,
वहां डिनोट करके बताएंगे देन
sure,
दैट विल बी
sure.
द मोर बेनिफिट एंड दैट विल बी
हाँ,
मोर क्लियर टू
sure,
अस.
sure. So this is IZ. So 1.946 is IZ. This is OZ. Okay, this is OZ. Now this is nothing but the predicted one. I am actually calculating in terms of SSE, not in terms of this only this OZ. Okay, because OZ is coming inside SSE. So SSE is a function of actual Y and OZ. Okay, so SSE, but I want to find out in terms of W0Z. So W0Z is actually included in IZ. So OZ is a function of, so OZ is a function of IZ. IZ is a function of W0Z. So this rule actually I have to find out. So SSE is a function of OZ. OZ is a function of IZ. IZ is a function of W0Z. Okay, let me write it here. So SSE is a function of F1, I'm writing OZ. OZ is a function of F2 of IZ. Then IZ is a function of W0Z. So what I have to do, that if I want to find out del SSE del W0Z, then I have to include this OZ, I have to include this IZ, because SSE is not directly a function of OZ. It is a nested function. Is it okay? Everybody understood? Please tell me. Is it okay? Mr. Amar? Mr. Amar, is it okay? So now if you can actually create one derivation, then actually it will be easier for you to derive the other derivations. Okay. So del SSE del WAZ. Okay. So this is del SSE del OZ, then del OZ del IZ, then del IZ, then del WAZ. Acha, what happened, Mr. Amar? You are not talking. Are you there? Yeah. Okay. ठीक है. Okay. Then next is del SSE del WBZ equals to del SSE del OZ, then del OZ del IZ, and then del IZ, then del WBZ. Okay, so these are the things. Now, what is del SSE del OZ? That is nothing but summation of yi minus yi hat. Then what is del OZ del IZ? It is actually, so del OZ is a sigmoid function. So it will be sigmoid IZ into 1 minus sigmoid IZ. And what will be this particular del IZ del OZ? That is actually 1 because it is having only 1 associated with this. Okay, so this is the first one. So this is the first one. Next is this one is summation of yi minus yi hat multiplied by sigma iz, sigmoid iz 1 minus sigmoid iz multiplied by what it will be? It will be OA, output of A. Okay, similarly this one will be summation of yi minus yi hat multiplied by sigma iz 1 minus sigma of iz multiplied by OB. Okay, so these are the derivations. So you can write now. So you can now write that you can now write W O Z new W0Z new. Okay, it will be W0Z old minus learning rate into this del SSE del W0Z. Similarly, W1 WAZ new will be W old AZ minus eta into del SSE del WAZ. Then WBZ new will be W old BZ minus eta del SSE del WBZ. Okay, got it? In this way. So this will be updated. Acha, next is that if you look at the next level, this particular at the input level, at the input layer. So let me just give you one idea. So del SSE, okay, del W0A. That means input node to hidden layer node A. Input layer bias node to hidden layer node A. How you can do that? It will be del SSE. So you have to start from that OZ. Okay. So it will be coming as del OZ, del OZ, del IZ, del IZ. Okay. Then del OA, then del OA, del IA, then del IA, del W0A. Now this is the first one is yi minus yi hat multiplied by sigma of iz 1 minus sigmoid iz okay. Then del iz del oa is 1, sorry, that will be WAZ, del IZ, del OA, del IZ, del OA. Acha, that will be WAZ. Yes, WAZ multiplied by sigmoid of IA 1 minus sigmoid of IA, and finally it will be 1. Similarly, del SSE del W1A, that will be coming as, all the things will be similar, del OZ, del IZ, del IZ, del OA, del OA, del IA, del IA, then del W1A. So all the things will be same, but only one term will be different. 1 minus sigma IZ, WAZ, sigma IA 1 minus sigma of IA multiplied by x1. Okay, so in this way, so all the updates will be there in this way.
So वापस उसको ना ये इसमें 5 derivatives that has been multiplied.
Yeah.
ये इसको फिगर के हिसाब से वापस del SSY del WA
Exactly.
इसको वापस फिगरेटिव
हाँ.
हिसाब से where del SSY del OZ I by del
हाँ.
IZ del IZ by del Y इसको
हाँ, so this is
फिगरेटिव में सर वो वहां लाकर whenever you will explain, then it will be more clear.
हाँ, okay. But here that here in this
इस पर
particular,
इस पर
so basically from the output layer now you are going to the input layer. Earlier it was from the output layer, it was on the hidden layer.
Earlier it was from input layer, then hidden layer, then final with the integration
so
with
that
the
was feed forward.
activation function, then output. Now it is
that
propagating
was
back ना, तो back में 5 आपने डेरिवेटिव आपस में मल्टीप्लाई कर
exactly
दिया, वो वन
exactly
स्टेप बाय स्टेप में कौन से कहाँ किसको डोनेट
So
करते हैं, that
here
should
it
be clear
is.
to us.
Yeah, I'm coming to that. So first is del SSE del OZ. Okay, then del OZ del IZ. Okay, so in this way it is coming. So here SSE equals to f of, so it is already there. So now we are coming to input layer. Okay, so this is okay, this was up to hidden layer, then up to input layer. Okay, now basically what is happening, okay, here del SSE, so this derivative is now del SSE del W0A. Okay, this one I want to find out. This one I want to find out, that what will be the update. So del SSE del W0A. Okay, so now what I'm going to do, that F1, F2, F3 to tha hi already. Now F4 is actually sorry, IZ, we have come to IZ. Okay, now after IZ, basically what I have to do, that IZ is the input to this one, right? Now input to this one is output to the output of the hidden layer nodes. Okay, that means IZ is function of, okay, IZ nahi, this will be, I'll be writing at OA. Okay, so that will be starting at OA. So output of A, output of node A. So output of node A will be function of input of node A then input of node A will be function of W W0A. Okay, in this way. Now connection between IZ and OA, what is the connection? So IZ is actually a function of OA. So this is F4 and F5. So IZ is a function of OA, right? And that OA is now function of IA, and that IA is a function of W0A. So in that way, I am developing the chain rule. Is it okay?
सर इट इज ओके बट अब पीछे से बैक्स होते ही आप वेट मतलब मींस SSC बाय WOA आया
अच्छा,
फिर
okay, okay.
नहीं,
So let me draw the
नहीं, इसके
diagram once
बाद
again
ये
here.
नहीं सब प्रीवियस फिगर जाइए ना
हाँ, let me draw it once again. Okay, so here it is x1, then x2.
माय क्वेश्चन इज आफ्टर गेटिंग दीज SSC बाय W डिफरेंस आप सब में
हाँ,
OA A1A उसके बाद ये सब इतने सारे मिलने के बाद व्हाट इज द मोटिव बाद में क्या करना क्या इसको है
हाँ. Now this is the del SSE del WA you are finding out. And weight updation rule, what is the weight updation rule? Weight updation rule is basically, here I have written now weight updation rule. Just check. So what is happening that this is giving you the new weights, changed weights, updated weights.
वो सारे वेट्स का फिर इनको कैसे इंटीग्रेट कर रहे हैं आप सब
Now the thing is, based on this, again feed forward calculation you have to do. Okay. So once the new weights you have got, you have to do the feed forward calculation once again. So this will give you another prediction. Then that based on that prediction, then again propagate the error to the input layer.
ठीक है ये थ्रू एंड फ्रो चलता रहेगा टिल
हाँ, through and fro चलता रहेगा. Okay.
टिल
So until till there is no change in the this particular weights.
till
You can
derivative with respect to output with variables equal to 0. I think is it right?
that means that is the thing, because W new will be very small or W new will be very similar to W old whenever it is happening for suppose certain iterations. Suppose for the next 10 iterations there is no change in the weight, that means there the derivative is actually coming to 0. So till then you have to do. Okay, that is the stopping criterion. So here what is happening, so let me just discuss once again. Okay, so here it is A, it is B, and it is 0, 1. This is 1 output Z. Okay, so this one, actually no, not this one.
Whenever you do a cancellation, you have to scan the passenger at the time of the cancellation. You will maintain the count accordingly. What is the static cancellation count? Whenever you do a cancellation, okay, then you can.
So here what is happening? This is W0B now, and this is W0A. So now what is happening? That here it is OZIZ. This is IAOA, right? So first, so this is giving you the SSE. So SSE with respect to OZ, OZ with respect to IZ, IZ with respect to OA, OA with respect to IA, IA with respect to del W0A and W0. So this is coming as, so I'm telling you, let me just draw something here. So these to this, these to this, these to this, this to this, and this to this. It is happening. So this is del SSE, del OZ, okay, del OZ, del IZ, then del IZ, del OA, del OA, del IA, then del IA del W0 A. Okay, so in this way, this is the chain rule.
सर लास्ट
Is-
लास्ट वन
हाँ।
थोड़ा सा कर डेल आई मतलब ये आई और डेल ओ ए ये लास्ट वन वाला वन वाले पे इस वाले पे सारे क्यों टर्मिनेट हो रहे हैं? ये है ना अपना क्या कहते हैं ये थ्रेशोल्ड है क्या बोलते हैं इसको
Nah,
नहीं।
bias node.
हाँ बायस
So, but bias node and A, that connection is having one weight, right? That we have to update that also, na?
नहीं ठीक है मतलब
Weight
वो
को तो update करना पड़ेगा. Weight को तो update करना पड़ेगा ना? Because I cannot update input. ठीक है ना? I cannot update input. क्योंकि input तो वही है, input output combination तो same रहेगा. Getting my point? Input output का combination same रहेगा. Okay, input I cannot disturb. What I can disturb, I can actually update the weights.
अच्छा मतलब सारे के सारे आकर के वेट सारे के आकर के
So now basically I am telling that the algorithm will be kind of, okay, so backpropagation algorithm will be that while this W new minus W old by W old, okay, it is having a certain, suppose 1e minus 4, okay, so till then it will run, okay. So W new minus W old divided by W old, that ratio when it is more than 10 to the power minus 4, update W, so W new equals to W old minus the learning rate multiplied by del SSE del W old, and this del W old में ही सब कुछ आ जाएगा. All these weights will be coming. So this is the algorithm. Is it okay? Whenever it is less than 1e to the power minus 4, then it will stop. Is it okay? So let me just show you one implementation using NumPy. So that NumPy, if I am using NumPy, then it will be easier for you to actually understand that exactly what is happening, how it is happening. Okay, and we'll be using for this classification. Okay, so classification, there is small change. So classification problem. Okay, so let me use different color. So for classification problem, what will be my error criterion? Classification error function means instead of SSE, I cannot use SSE. So for classification, we'll be using this kind of. Can anybody tell? So error will be given as 1 by number of classification example divided by minus ye log of h of this thing for xi. Okay, so for I equals to 1 to m minus 1 minus yi log of h w x I. What is this w? W is basically hw is 1 by 1 plus exponential w transpose minus w transpose x. Okay, that is the sigmoid function. Is it okay? And then change. Just this will be the change, and rest all everything will be same. So it depends upon activation function is sigmoid. Now, if you use ReLU in place of sigmoid function, you will be getting one only. Why? That ddx of ReLU x will be ddx of max of 0 comma x, and that will be nothing but 1 when x greater than 0. When x less than 0, it will not be coming. It will not be x less than 0, it will be 0. Is it okay? So in this way, basically, this is changed. Okay, understood or not? Could I make you understand? Could I make you understand? Please tell me.
Yes, sir.
Okay. अच्छा, so let me just रेलू के बारे में कम एक्सपोजर है. Okay, no issues. रेलू actually, what is the usefulness of रेलू? It is a kind of linear. Okay, what is happening that if you are derivating or if you are differentiating, if it is x is more than 0, then it is giving you 1. Okay, so basically it is not changing anything. मतलब ये जो sigmoid sigma into 1 minus sigma is coming. If it is some other kind of tan h, if it is, then also something will be coming like this. So all these things will be, means you are actually avoiding all these kind of complexities. Simple, it will be 1. Okay, that is how it is coming. Acha, let me show you one example of this NumPy based implementation, and then we'll be going for PyTorch based implementation. Okay, so acha, in the next session, means after lunch, I'll be starting this probabilistic PCA, probabilistic principal component analysis. I had planned some more things, but I was thinking that okay, let me stop it here itself because this is going to be more and more complex. There are many things to do actually. So I was thinking that let me stop it somewhere easier, so that you will also be able to, because what happens, you know, that if I am going too much difficult, then you will feel lesser interested. Okay, so your interest might go, okay, this is becoming, because this is really complex things. These are really very complex things. We have to actually sit, we have to actually implement those, okay, one by one. So that is why I'm stopping it here. Okay, means in the next session I'll be, yeah, in the next session I'll be going for probabilistic PCA, and after that, yesterday's that data visualization, that will be completed. Okay, so this is my plan. Okay, just 1 minute, let me find it out whether. Let me find it out. Yes. Okay, so yes. Also this one and another one, let me also. Okay, so one from scratch, let me just tell you. Okay, so this is a classification problem, and classification problems are actually little bit better to understand that exactly what is happening. So let me share my screen. Okay, so can you see my screen? Can you see my this coding?
Yes, sir.
Okay, VS Code. Okay, Acha. So let me import the packages first. Okay, let me generate the data set first, few of the data sets. So you can generate some kind of synthetic data sets from using this sklearn.data sets. Okay, you can actually some example data sets are example codes are there. Okay, or you can actually have your own type of data you can actually generate, like for clustering, for classification, any kind of data actually you can generate. Okay, so
How many inputs are there here? X, Y, I think.
yeah, it is only two variables. It is only two variables. Okay, two predictors, x0 and x1. Okay, means two input variables. Okay, and your output is one. Okay, that means one class. That is binary classification. But for binary classification, we'll be going either by this kind of either as I told that how we actually will be changing the classification error function. Okay, so for that you can go by entropy loss or you can go by softmax. Okay, so both are possible. So this is the kind of data I'm having, and you can understand that you cannot have a linear boundary kind of thing. It's not possible, isn't it? It's not possible. So what you have to do, that you have to actually so if you go by logistic regression, then also it might have little bit problematic in classifying them truly. Acha, for classification purpose, how you can measure the performance of classification? Can anybody tell me? How can you measure the classification performance, classifier performance? That you have created a classifier. Okay, so how will you actually tell that it is a good classifier? What are the metrics available? Can anybody tell?
मैट्रिक्स का तो नहीं पता सर, एजेस को देख करके पता करते हैं कि बाउंड्रीज कंडीशन किस, मतलब किसके बाउंड्रीज कितने वो आई डेटा गिर रहे हैं, और ऐसा तो नहीं पता है.
No, I'm not understanding. What did you tell? What did you tell? So what I'm actually pointing at, let me clarify my questions. Okay. So question is that let me go back to the my slides. Okay. So slide में जाके मैं बताता हूँ. Okay. So where is that share screen? Share screen. Stops sharing. Share this one. Okay. So let me describe it here. So performance metric for linear regression is how do you check that how good your model is? Okay, that is R square. Okay, so R square is 1 minus SST by SST. Okay, so if you are having any idea about this particular SSE, SST, they are coming from ANOVA. If you are having little, if you have studied little bit of this statistics anywhere, okay, then you'll be finding out these are relevant. Okay, otherwise it is a little bit difficult to understand. R square. So R square, as it is squared, okay, so it cannot be negative. So this will be greater than equals to 0, less than equals to 1. R square. Okay, and higher the better. Okay, higher the better. There is another metric that is known as RMSE. RMSE means root mean square error. Okay, so under root mean then squared error. Yi hat square. Okay, RMSE. Now RMSE will be always greater than equals to 0. Okay, greater than equals to 0, and it is lower the better. Okay, then I can have something called as MAPE, mean absolute error. Okay, so it is 1 by n, then mean, that is summation, okay, then yi absolute, yi hat, okay, multiplied by 100 by 100, multiplied by 100%. Is it okay? In this way, different types of, these are the performance metrics. Okay, now these things are not, they are not applicable in case of classification. Acha, tell me that how many of you are actually exposed to basic machine learning? Basic machine learning, statistical modeling, and all these things. How many of you? Can you please speak up? So if you are, then please raise your hand. Better to raise your hand. How many of you can understand this? What is this R square, RMSE, MAP, and all these things? Studied in PG as in project, okay? Anybody else? Anybody else?
सर इसको ग्रेजुएशन में भी था ना ये अपना कम्युनिकेशन में, that was in communication signal to noise ratio where we perform the
signal
quality
noise
of the
ratio.
signal we are getting at the receiver side, then it is through the signal to noise ratio where we also calculate the errors.
SNR, yes.
SNR. The performance
yes.
of any communication signal, how much it is getting, how much distorted, how much it is good or bad, it is only judgment on the
Exactly.
SNR.
Exactly.
Same way here it is RMSE and R square.
RMSE and R square and all these things. Yes, very good, very good. But for classification, basically classification metrics, okay, I think you might have heard of something called as receiver operating characteristic. If you are from electronics, electrical background, in digital signal processing, this is a very, very important kind of metric. Okay, okay. So I think, later I'll talk about this while at the end. Okay, receiver operating characteristic curve. Okay, ROC. So this is R, this is O, this is C. So basically, what happens that I have to create something called as confusion matrix. Confusion matrix. Confusion matrix is telling me that what is the actual side, okay, actual side, and another is predicted side. Okay, now suppose if it is a binary classification, okay, suppose if it is a binary classification. So binary classification means either it can be 0, 1, or it can be positive, negative. So this kind of generally what happens that we call it as positive and negative. So yes, acha, okay. So later we'll discuss that whether any course is possible, program is possible for you to teach this particular ML, okay, basics of ML till basics of DL, because this probabilistic actually comes under this advanced level of ML DL. Okay, let me come to this. So when your response is actually positive, and then the predicted is also positive, okay, then it is called something as true positive. When actually positive and predicted also positive. So basically what happens that suppose I want to predict that whether tomorrow rain will happen or not. Okay, so I am basically taking some kind of data points. Okay, I'm doing this survey. So somebody told yes, it might happen. No, it might not happen. Yes, then no, then yes, then yes. Okay, as a now predicted is basically this is the predicted one. This is the predicted one. Now actually suppose I'm having, suppose in the for each of the cases I'm suppose I have got this is 1, this is 0, this is 1, This is 1, this is 1, then 0, then 0, then 1. This kind of thing. So what is happening? That 1, if it is positive, so 1 is positive and 0 is negative. Okay, so actually negative, but predicted is positive. Actually positive, predicted is negative. Actually positive and predicted is also positive. Actually positive, predicted is also positive. Actually negative, predicted is also negative. So in this way, basically it is coming. Now, if it is actually negative and predicted also negative, then it is called as true negative. So TP equals to true positive and true negative, Tn equals to true negative. True negative. Okay, now the problem, so these are the basically good performance of your classifier. Means if you can tell that if you can predict positive as a positive, and if you can predict negative as a negative, then it is good. Problem is with the other two scenarios. Okay, so actually it is positive. Actually it is positive, but you are predicting it as a negative. Okay, then you will be calling it as false negative. Okay, and actually it is negative and you are calling it as, you are predicting it as positive, then it is called as false positive. Now these two are the misclassification. So FP is false positive and Fn is false negative. Okay, now FP and these are the misclassification, and these two are the true classification. Okay, so in this way, now what happens that there are few more terms that will be coming, something called as FPR, false positive rate. False positive rate. And another is TPR, that is true positive rate. Okay, so expression for this, I'm not able to find it right now. So have you come across these things? Can anybody please confirm? Can anybody please confirm? Have you come across these things? Can anybody please confirm me? No. Acha, okay. So let me just, we have heard false positive. Yeah. So I'm thinking to make it little bit more detailed in the next class. Okay. So because abhi to time hone ja raha hai already. So TPR. Okay. So TPR is actually TP by Fn. Okay. So this is TP by TP plus Fn. Okay. So TP by TP plus Fn. So TP by TP plus Fn, that is actually positive, that is actually positive rho. Okay, so that is true positive rate, and false positive rate is coming as, um, okay, false positive rate is, FPR, it will not be coming, it will be actually TNR, so true negative rate. So this will be, FPR is not required, it will be true negative rate. Okay, so true negative rate is Tn by Tn plus Fp. So Tn by Tn plus Fp, that is true negative, basically we are finding out. Okay, so true negative rho. So true negative rate is Tn by Tn plus Fp. Okay, now based on this, basically I'll be finding out. Okay, so specificity is this one, and this is called as specificity, or this is actually 1 minus FPR. Okay, 1 minus false positive rate. Okay, so 1 minus false positive rate. Now, if I can draw false positive rate by true positive rate, okay, then the classifier should show this kind of, okay, curve, and this curve is known as ROC curve. And steeper the curve, better is the classifier. So if it is suppose this one, or if it is suppose this one, okay, so best is this green one. This one is the best one. Okay, so this is what actually you have to do in case of classification, right? So so I'll be continuing this thing in the next class, next session. Okay, it is already 1:25, so I think you will be feeling hungry. I am also feeling very hungry. Okay, so we'll be starting at 2:30. Is it okay?
Okay, sir.
We'll be starting at 2:30. Okay, and let me just discuss about this particular neural network classification and regression a little bit more, so that you can actually work on that. Okay. Okay. Shinu, please stop the recording.
Okay,
Shinu,
sir.
please. Shinu, hello.